Hello everyone, it's June the 5th, Saturday. Saturday. Oh, kind of a bit dread Saturday, but on the other hand, also excited. Like, two happen at the same time. So we know it's not going to be something simple. It has been this way like for the past few weeks. It's going to be something like hard. Alright, let's take a look. Maximum performance of a team. You're given two integers, n and k, and two integer array, speed and efficiency, both of length n. There are n engineers, numbered from 1 to n. Speed I and efficiency I represent the speed and efficiency of the ith engineer respectively. When I talk about speed and efficiency, I thought they're talking about racing. And then I saw engineer, I was like, whoa, well, an engineer is about to race? Apparently not. Choose at most k different engineers out of the n engineers to form a team with a maximal performance. Performance is the sum of their engineer's speed multiplied by the minimum efficiency among their engineers. Sum of the speeds multiplied by the minimum efficiency. Return the maximum performance of the team. Since the answer can be a huge number, we're going to mod it, okay? So I have these. So I'm going to choose at most k different engineers. So I choose at most 2 engineers. And we're going to sum the speed and multiply by the minimum. So let's say 9, 7, right? They're huge. And the minimum is 7. So if I choose these two, I have to choose 1 and 5. So it's 6 times 7. That's only 42, right? That's not good. So we need to choose others. And because we're only using the minimum, so it's possible that 1, we choose 1 is actually the better solution. Okay, let's choose 10 and 8, right? So that's 18. 18 times 2, that's not good. Wow, where is it? So 10, I think we should choose 10, all right? If we can get something that's, let's say this, 9. Oh, but it's multiplied by the minimum. If I choose 10, the minimum is 4, which means if I choose anything larger than 4, yeah, we just need to make sure we don't choose anything smaller than 4, because if it's smaller than 4, then we'll go for the smaller. So we go 4. And then we choose whatever we choose, doesn't matter. So we try to maximize it. So we choose an 8. So 18 times 4. Right? What's 18 times 4? Isn't that 70 something? 72. I choose 10 and have efficiency 4, right? So it says efficiency is the sum of the speeds multiplied by the minimum efficiency. Speed 10, efficiency 4, and 5 with efficiency 7, that is 10 plus 5 times 4. What if I choose 8? Oh, 8, you have efficiency is 2, so you have to times 2, so 18 times 2. So if I choose 10, I have to go for 4, so it has to be something bigger than 4. So among these things, 5, 9, 7, right? 5, 9, 7. Yeah, so we choose 5, because that's the largest. And then 10 and 5, okay. How about this one? Well, we can do the same thing. So the largest, I'll put emphasis on here because this one is choosing minimum. So if I say I want to pick the largest one, this one gives us 4. Oh, it's the same thing, but now we have 3. Okay, so 10 gives us 4. So I want minimum to be 4. Don't be even lower. Otherwise, it's not worth it, right? So something bigger than 4, so I have 5, 9, 7, right? 5, 9, 7, which means it's 5, 9, 7. So we choose this, 10, 5, and 2. Right? 10, 5, 2 is 17. Then we do 17 times 4, which gives us 68. If I have 4, exactly the same thing, so we're going to pick everything that's bigger than 4. So it's going to be 10 plus 2 plus 1 plus 5. That's 18. 18 times 4. 10 to the 5th. Okay. 1 to n, k, efficiency, both to n, speed, efficiency. All right. Got a question. What is your idea? Well, I don't know. If k equals 1, right? If k equals 1, then that just means to find the largest product from here times here, right? Which in if k equals 1 is actually this is 10. Let me write it down. 2, 10, 3, 1, 5, 8. 5, 4, 3, 9, 7, 2. If we choose 1, that is 40. 40 is the biggest. So if we choose 2, however many we choose, efficiency will be the minimum, right? Efficiency will always be the minimum among the chosen one. And the chosen one will always be, if we want to go, say, greedy, want the speed to be the maximum. All combinations. Ten to the 5th. No clue. That feels to me still a DP problem. So let's say I choose the first one. So each person can either be inside or outside. I can be in it or I can be out of it, right? That's the gist. So if I'm in it, then I have a efficiency. Then say like we start from 2 and 5. Let's say efficiency is 10, right? So we pick 2, 5. Now we have a new adding in, but it's not sequential though. It's not sequential. Yeah, it's not sequential, which means it could be any combinations. That's fine. So like the next one, 10 and 4, say I can be in it or I can be in, so I can say, now I feel like a different problem because it doesn't have to end at the one before us. So we then pick the maximum. So you pick the maximum on speed, and we have an efficiency, or pick the maximum on efficiency. Well, pick the maximum on efficiency doesn't really work unless, yeah, pick the maximum on, if k equals 1, that's a trivial case, right? If k equals 2, and I say we pick the maximum on efficiency, then get some result. But the thing is, sometimes 1 is better than 2. Maximum efficiency, because maximum efficiency, then if I need to pick another one, then it's no longer maximum efficiency. So I think efficiency should not be taken as higher order, because like no matter what you do, if you pick more than one per people, then the efficiency cannot be guaranteed to be the maximum. So the maximum is useless, right? It's not useful. So the efficiency is just to make sure that the minimum we pick is big enough, right? So we shall focus on the speed. Now in terms of speed, it is possible to have a scheme with, let's say, efficiency is all 1 except for 1 is 100, and for speed is everything is the same, right? Everything is the same. Like efficiency, speed, everybody's 1, and efficiency, everybody is 1 except for 1 is 100. And then say if I do k equals however large number, then the best solution is to get k equal to 1, because if we do k equal to more than 1, then we do minimum efficiency, then efficiency drops, right? So we do have to find a maximum with only one person, right? A maximum with only one person. If the maximum with one person has the efficiency that's not the maximum, right? If the max performance with k equal to 1 relies on a person whose efficiency is not the maximum, then we can, as we add more, we can use that as the benchmark, right? We need to add more. We have choice, right? We have choice because we think that the maximum with one person must be involved. Let's think about this. If the maximum with one person, we have a speed times efficiency, and those produce the maximum value among everybody, right? And then if we want to add another person, now add another person, definitely we can boost the speed, right? So if we boost the speed while not reducing the efficiency, then that is guaranteed to be also the maximum. Is that correct? Well, what we're talking about is two people maximum, so we have two sums on the speed, right? And we potentially two sum on the speed, and then we have times something that's the minimum on the efficiency. And we know that if we times the efficiency that's associated with the one person scenario, then we have the maximum plus something else, right? Maximum plus something else. Then we just need to make sure we pick the largest on the speed, right? With the largest on the speed whose efficiency is bigger, whose efficiency is bigger than the original one. And then that will guarantee to be the largest. Or will we have a different situation? Well, what other situation do we have? So we have a speed and an efficiency with one person, k equals 1. Now, if we do k equals 2, we need to add another person to it, right? We add another person to it, the situation is, actually it does matter. So let's say another person added. If the person's efficiency is larger than the original efficiency, right? If efficiency is larger than the original efficiency, then we will always use the original efficiency for the multiplication. And then in that scenario, we want the speed to be the maximum, right? So the maximum speed whose efficiency is smaller than the original one. And then, so that's one scenario. The next scenario is it's actually larger than equal, right? Larger than equal. The next scenario, if the new efficiency is smaller than the original efficiency, it's possible. If the new efficiency is smaller than the original, then we want, then we don't know. Then it depends. Then we have to check. And check and go through everything and to see if. So we need to do is the speed, the new speed, plus the original efficiency multiplied by the smaller efficiency. And how does that work, right? So I think no matter what, right? No matter what, if you pick one person, you get a speed and efficiency, right? If you pick two people, you essentially also get a speed and efficiency. The speed is just the sum of the two people, and efficiency is whatever the efficiency is. And that is a recursion problem, right? You got two people, you can combine them into one person, and basically we just combine two, and then we just kick out, right? We kick out, we get the length of the array a little bit smaller, right? A little bit smaller. Okay, so the length is a little bit smaller, so each time the problem is the same. It's the same problem, right? It's the same problem. It's the same problem. There are just way too many combinations for this. We have 10 to the 5th. 10 to the 5th. All right? If we do k, and that's going to be a gigantic number. Gigantic. Unbelievably large number. Unbelievably large number of options to go through. If we have a person, like one person is the most efficient, right? Combine people as well. And then we want to add a new one, right? Is it like a guarantee we have to add to this person, or is it possible that a new people can show up? Well, a new person will not be able to show, well, I mean, this person is already the maximum efficiency, right? When considering k equals 1, we have the most efficient, right? So if we want to get 2, so the question is, we have the most efficient, and if I have two people, is it always the most efficient plus something else? Or two not the most efficient combined? If the two not most efficient, they want to combine, right? If two not most efficient. So let's say we have, again, S0 times E0 is the max. Now we have S1, E1, and S2, E2. Let's suppose that S1, E1, S2, E2 combined together will achieve a better one compared to S0, E0 with something else, right? With something else. So when we combine S1, E2, so we do is S1 plus S2 times the minimum E1 and E2, right? Let's call it as E min. So it's S1 times E min plus S2 times E min, right? Let's just say E1 is E min, so it's just like it doesn't really matter. S1 E1, S2 E1, right? In that case, we know S0 E0 is definitely larger than S0 E0 is larger than S1 E1 and also larger than S2 E2. Therefore, S0 E0 is larger than S1 E1 and S2 E2. So it's larger than both, right? It's larger than both. Now I want to add something more, right? I want to add something more. Now when we add something more, if that something more has so hold on. If that something more is S1 E1, right? I mean, we can always do S1 E1. That's something more. Like the hypothesis is we can find something that's S1 E1 plus S2 E1 will be bigger. So now we say, let's say this one is bigger, right? And let's also say give S0 E0, and we're gonna add S1 E1 to it, right? We add S1 E1 to it. So when I add S1 E1 to it, there are two situations. Either it turns into S1 E0, right? Or like it turns into S1 E0 because we're times 0. So now it's a comparison of S0 E0 plus S1 E0. Is this one bigger? Actually, we don't know. All we know is S0 E0 is larger than S1 E1. It depends. That means E0 is smaller than E1, right? E0, yes, E0 is smaller than E1 because I say I'm going to put S1 E1 to it, and then we take E0. That means E0 is smaller than E1. So S1 E0 is smaller than S1 E1, but S0 E0 is larger than S2 E1, right? S2 E1. But how about their sum? Do not know. We do not know their sum. What if we take S0 E1? That means E1 is a smaller one. E1 is the smaller one. Then we still don't know. Wow, this is definitely a hard question. I don't have any clue so far. Embarrassing, huh? I'm gonna pick some from the speed, and we're gonna do the minimum value on efficiency, and it's the sum times the minimum times the minimum. So as we add more people, right? As we add more people, the efficiency, if we sort the efficiency, right? And if we pick the one with the smallest efficiency, that means we already have the smallest efficiency, then we can choose whatever we want, right? We can choose whatever we want. If our efficiency is the smallest, then we can pick the largest, by have to include this. So excluding this one, the remaining, we can pick all of them, add them together, so that can give us a value. Right? In this case, let's say we pick this, and we can pick 10, so it's 18 times 2, right? That's 36. Hold on. Alright, I'm back. Okay, let's keep the thought, right? We have the minimum on this, and then we have 36. Now let's say we want a 3 as the minimum. If 3 as the minimum, we must pick 3, right? And then we can pick the next largest one, that's 10. Yeah, because 10 is larger. So we have 13 times 3, that's 39. Oh, it got bigger. Next one is we pick 4 as the minimum. So 4 as the minimum. Then we have 10. We end up 10. So we're going to pick the next one. That is... Oh, actually, I cannot pick 10. My bad. We have to pick... Oh, we can pick 10. We just pick something that's larger than this. So now we pick something larger than this. So only option is 597. 597. 5, 9, 7. So we pick 5. Right? That's give us 60. So 15 times 4. Next one is 5. 5, we have 2. So we can only pick 9 or 7. Right? 9 or 7. So we pick 5. So 5 plus 2 is 7. 7 times 5 is 35. Next one is 7. We pick 7. We have 5. Only option is 9. Right? Only option is 9. Then, in that case, it's only 1. That's 6. Actually, 1 plus 5 is 6. That's 42. It's actually pretty big. It's 42. It's still not big enough. Last one, let's say we're going to pick 9. Which, if we pick 9, that's the largest. It's not possible to get 2. So, if we pick 9, we only get 1. That's 9. So that's therefore we say it's 60. Okay? So coming this, and do the same thing. That's what we say pick 2. Then we have 8. The remaining, they're all bigger, so we just pick the largest among the remaining. It's 10 and 5. So what we do is 10 plus 5 plus 8, that's 23 times 2. We got 46, right? We got 46. Now let's say the minimum is 3, right? If the minimum is 3, we must be including this. And we're going to pick everybody else, right? So we can pick 10. We can pick 5, right? We can pick 10 and 5. 10 and 5. That means it's 10 plus 5 plus 3 times 3. Give us 54, a little bit bigger, right? And now we say it's only 4. So we have 10, and we're going to pick 2 more. So we have a 5 and 2. So that's 7 plus 10 times 4. 68, right? I think this one looks promising. Looks promising. I mean, we just need to figure out a good data structure to get this to work. I'm thinking about this test case. Let's see if this test case we can work it out. Like the test case I'm thinking about is everybody's 1. Everybody's 1, right? And everybody is 1 as well. But one of them is 100. And so we're going to pick 6. We're going to pick 6. And this should be 100. Should be the same as picking 1. Right? So if we run the code, it should give us 100. Yeah, it's 100. So how do we handle this? We say, let's say the minimum is 1. Ooh, we have replication. How can we handle replication? Minimum is 1. And say we can pick anything. We can pick 6. We can pick all of them. That's give us 6. Alright? So minimum is 1. Minimum is of certain value. Yes, that means we should need to do a dictionary with efficiency as the key. And we have the speed. The speed is going to be a list, right? Sorted list. And then we're starting from the minimum. and we can get a certain number, and we can combine all the lists together. When I count, right, how many do we need? So we have the efficiency is the key, and efficiency is the key, and we have values. Those values are speed associated with the efficiency. If I say this efficiency is the minimum number, right? If that is the minimum number, then what happens is we're going to look through everything larger than me, efficiency-wise, larger than me, and we have a pool of numbers, right? All we want to do is find the maximum. So we take the maximum of the values associated with the current efficiency, for sure. And then for everybody else, basically we take that one out because we have to choose it no matter what. So we have the remaining, all the numbers, and we need to find the maximum among them. Right? We need to find the maximum among the top, like the top few among the rest. Is there a better data structure to do this? Like we can constantly popping out the maximum value, right? We pop out the maximum value, and then we need to pop out the max among the rest of everybody, and now we have a list of the max values. Then we take the max of these maximum values, like the top, like we have the rest, so we pick the max among all of them. Also depends on like how many. So what I think is, if after I pick out the one I have to choose, now we have the remaining, which is efficiency, my current efficiency, and all the efficiency larger than my current efficiency, right? We have all these options, right? And then with all these options, we need to find the maximum sum among them with a given number of things, right? If the given number of people to get, if that's smaller, then if that's the same as the number option we have, so we just pop out everybody. No, we have to go with the maximum among them. It's a must. We have to go with the maximum among them. Like every time when a pop out is going to be a maximum. So how do we do? What is a good data structure? I'm thinking about priority queue, right? Priority queue, but this priority queue has to be like a global priority queue. Global. A priority queue. I need a priority queue that is because it constantly changes. That's the thing. It constantly changes. Like if I swap, maybe it's we have a minimum, right? Let's go with the smallest. But we're talking about going through all n. What does not mean? It's the maximum is n. Try to go through every single one of them, and we don't know if we find it. Do we know we find? We don't know, right? We go through this minimum, and then we find the maximum, the maximum sum, and then we move on to the next one, right? And then some of the value just gets kicked out, right? Some of the value gets kicked out, so we cannot use those anymore. And we're shrinking the search space. We are shrinking the search space. Each time we move, some gets leave out. Okay, that's shrinking is good. Shrinking is good. So we can go from the smallest, and then we find the value, and when that's done, we remove the smallest, because the smallest is just gone. We don't need it anymore. And now we go to the next one, right? We'll go to the next one, and that's everybody, right? Because we removed this already, so that's everybody. That's just a lot of sorting and a lot of, yeah, how can we handle this? That's just way too much. Ten to the fifth. No, efficiency is 10 to the eighth. Efficiency is 10 to the eighth. I pick the smallest, and then the rest. Binary search. But it's like, we have to remove, right? We have to remove. That's the thing. The remove part is, it's not easy to do. The remove part. If I sort the speed, right? If I sort the speed, and then I have the efficiency, I sort the efficiency as well. So we got the smallest efficiency, but we kept a mapping from efficiency to the actual speed. So if I pick one of this as the smallest efficiency, then we take the maximum, right, associated with this. Okay, so that has to be. Now the remaining we have a list. We need to find the remaining. Now the remaining will be just the max at the top. Yeah, it will be just the top. And then, good, we can get it. Now after this one is considered, right? After this minimum is considered, I need to remove. I mean, we can remove this, which is easy. Okay, we remove it from the dictionary. That's O1. But how do we remove the ones in here? That is a good question. We don't remove, right? No, we still have to remove, but we're always going to go from the top down, right? The top down. So what we say is, if we pop the top, if the top is good, right, we record it, and we move on to the next one, and we read it again. What, like 2 priority queues? So we pop one, we put in another priority queue, we pop one. If that one belongs to the one already deleted, don't do anything. We keep popping until we pop enough, right? And we put it all into the other one. And okay, So that's next. And then we do the next one, next the smallest, pick the one out, and which priority queue to start popping with. Oh, we have to start popping with ones, right? Because that's the maximum we pop the other one. So pop this one out. But we need to merge these two, right? We have to merge two priority queues. Merge. How do we do this? Then we need to pop it. But if we pop it, it's going to be, we're talking about, we want to do a linked list from the max on the link, right? And then we just go through from the front. And if it is not, we just remove the node. We'll go to the next one, and go to the next one, next round, go to the front. A linked list. Maybe that is a linked list. Because if it's a linked list, then we use this to get the max value, right? We get the max value for this, so we save it on the outside, and then we go through the linked list from the top down. So from top down, if this one, if the value has efficiency the same value, we take it. So we go from the largest to the smallest. So we take the largest to the smallest, whose efficiency is larger, equal to this. And once we're done, right? Once we're done, we get the current result, and then we remove this. We move on to the next one, right? Move on to the next one. And then we need to be finding stuff larger equal to this. So we go back to the linked list. So the front of the linked list, now if anybody is this value, smaller than this, then we remove it, delete it. So which means, this will mean we're gonna go through each one of these once, and we will go through this n times. So I think this one we can reach O n n. This is a capitalized N, lowercase n, plus O n log n on this, O m log m on this, O m to produce the linked list. Does Python has a linked list? And maybe there's like a better a deck. Oh, a deck is a double-ended linked list, right? Yeah. But I don't think you can linked list. I don't think a stack works. Yeah, it's gonna be ON if it was a list. No, it's not a deck. It's not a queue. Of course, it's not a stack. Yeah, I'm thinking about creating our own linked list. Really, linked list? The deck cannot work? Deck doesn't work. What I want is I traverse through a sorted list, and once I find something that does not belong, I want to remove it, so I don't have to traverse it again, right? Otherwise, otherwise it's going to take a lot of time. Let's give it a shot. So, not sure. Feels like in a timeout, but we gotta give it a shot. Yeah, feel like it's on timeout. It's very convoluted. I feel like. Anyway, so right. So what do we do? I don't have to sort. I just need to pick the maximum among them, right? So we have efficiency, and we have speed, and what do we need is. I just feel like I can do this with a priority queue, right? With the speed is the first tuple and the first one, efficiency is the second one. And we would do a maximum queue, so we do a minus, right? The queue pop out is going to be the maximum. If it is the one we've seen before, then we just ignore it. If it is not, that's the problem. If it is not, then we just push it to something else, right? We push it to something else, and after we do that, we just need to merge the two. We need to merge the two lists. We merge the two lists, and maybe we have like a merge head queue, heap queue, not head queue, heap queue. I have heap, replace, pop, and return the smallest, and also push the new item. Not merge multiple sorted inputs into a single sorted output. Similar to sorted. Maybe we can use merge. Yeah, the remaining we can just merge them. N largest, n smallest. N largest from. So well, we take the top, right? If it's not, if it is, then we record it. Oh, we cannot push it back. Oh, we cannot push it back because if I push it back, then if I push it back, then it will pop to the top again. So every time it will pop up the same thing. We want to know the next biggest. All right, the next biggest. So we have to put it somewhere else, right? Put it somewhere else. Put it somewhere else, and we just keep pushing, and we merge the two, right? And then we merge. And afterwards, we merge the two. Let's try this. Maybe this one will be faster. I don't know. Import heap queue, right? So I think the idea is heap, right? Heap equals for E efficiency, for speed, efficiency in the zip it, speed, and efficiency, right? And speed is going to minus S and E efficiency, right? So that's the heap, and after heap we need to heapify it. So in the heapify it, so in the heapify, heap dot heapify heap queue dot heapify, right? Now we also need to create a mapping how should we do that? How should we do that? We create another mapping. Yeah, so we're gonna say efficiency speed map. Right, because this, and we say for E, for SE in zip, we zip again, speed, efficiency. Wow, this is going to take a long time. I mean, these two already take like ON. So for S and E in this, we say, let's say ES map, right? ES map. ES map, actually, are they all larger than 0? Yeah, larger than 1. So I can actually use a default dict. Let's do a default dict. So from collections, import default dict. Right, and then we're going to go to default dict. Default dict int. Right, so we say efficiency equals max es map e and s. So after this, we get the maximum of everybody, and then we need to sort efficiency. My God, how we have to sort it now? So like what? For E in sorted efficiency, right? My God, now we have sorted efficiency. So it's like ON, that's log n, ON plus log n plus ON plus ON log n. Okay, so this ON log n. And what? It's sorted. So we get E out. So we know the sums, right? Sums, speed sum equals ES map E, right? Then we need to go through for k times, right? Temp equals this. I'm going to say for this in range k minus 1, because we already take 1 out, right? So and k minus 1 times if heap, right? If heap, then candidate equals heap q dot heap pop heap, right? So it's actually candidate speed and a candidate efficiency equals this. And if else, we just break, right? So we have the candidate. Now we say if, and we have to use another one, which is used equals a set, right? And then I'm going to say if candidate E is not in, no, if candidate E is larger, right? If it's larger or equal to current E, actually we don't need this, we'll just say larger or equal to current E, then speed sum plus equal to minus candidate S, right? And then we used it, then we, yeah, so we use it, but then we say if candidate E is equal to E, is larger than E. So if it's larger or equal to E, we can take all of them, but then only if it's larger than E, that's the one we're going to say. So we're going to say temp dot append candidate S and the E, right? So we go through each one in a heap queue, take as many as we can, right? As many as we can, and then we discard the one that has the same level. And once it's done, right, temp dot, now we're gonna say heap, right, heap equal to, I think we can do the merge, heap q dot merge heap, the remaining of the heap, and the temp. So we merge them together, and we go back to check the next efficiency. We also need a result, 0, right? And then we say res equals max res e times speed sum, right? E times speed sum. All right, that will be it. I'm just thinking maybe we don't have to do this part. Yeah, I don't think we need to do this part. I can save. Let's save this mapping. I don't think we need this mapping. We do need this, right? But it doesn't matter. It doesn't matter. We just say. Speed at s at e 0, right? And then we're gonna go through k, all of them. We're gonna go through k, so all of them. And if a heap, I'm gonna pop it out. If it is larger, oh, that's the thing. That's the thing. We have to have the e. We have to have the e. We cannot not have it. But hold on a sec. Hold on a sec. Our minimum efficiency. So E is our minimum efficiency, right? If the top, right? If the top, they have efficiency already larger than E, then we can like upgrade the E immediately. Which means, okay, so the minimum efficiency we're looking at is E, right? That's what we currently looking at. This is the minimum efficiency, is E. So that's the minimum we're going to look at. And then we go through this. And if it's larger than E, then we add it and then we push it to the temp. No problem with it. If it's smaller than E, then we just remove it. We don't even consider it. If it's equal than E, then we need to see that we add it. But if it's equal to E, then we add it. And once we are done, hold. I think we have something. So current efficiency equals min efficiency, right? Min efficiency. That's the current efficiency equals min. And then we'll go through this. Say if E is smaller than current efficiency, then we continue. Now we reach current efficiency, then we go. E is equal to current efficiency, so we can say if it's larger or equal to E, we always do this, right? It's larger or equal to E, we always do this. If candidate E is larger or equal to larger or equal to the current E, then we add it and we say if it's larger than, then we append it. And if it's equal to, then we ignore it, right? And we also want to know what's the current E, right? Current E. So as we go through, this E is the smallest. The smallest E. We go through the efficiency. This is the smallest E. Hold on. If we sort it, then we have the smallest E. Then we're going through. We can use binary search to find the next E. We don't have to go through them one by one. Yeah, current E is this, right? And then we just say this is current E. And then we go through. After we go through, we can collect the next E. The next E, how do you collect the next E? Based on the current E. Like the current E will be whatever is the smallest among these guys, right? The smallest among these guys will be the next E. Yeah, that will be the next E. If the smallest is the current E, then we binary search to find the next E. Otherwise, we can leapfrog. Like if the candidate E, all the candidate E are larger than my current E, then I can leapfrog to the next one. That'll be the candidate E, like the next one of the candidate E. And we do this until I don't know until when, until we run out. Until the heap is gone. Yeah, until the heap is gone. So we can just this and heap equals. We can say while heap, right? While we have heap, right? And don't have to do this, but we do have to do sorted efficiency equals sorted. I would just say efficiency dot sort, right? And then this is going to be efficiency 0. Right? That was what we start with. So I'm going to say for k values, well, no, it has heap. So we say if heap, we still need f heap, and then we get it out, and then we say if candidate E is larger or equal to current E, yeah, current equal to current E, then we add it. Where is speed sum? There's no speed sum, so we have to do speed sum is 0. Next E, it's not next E, it's the used, the min used E is 0. No, this has to be a large number. Math.inf port math. Okay, so now we go k, right? And then we say if heap, pop it out. If candidate E is larger or equal to current E, that's our current minimum. And then speed do this. If it's larger than current E, right? If it's larger than, because we have a current minimum we're looking at. But if it's larger than what current we're looking at, put it in. If it is equal, then we don't put it in, right? And once this is all done, we can say min used E equals min used E and candidate E. This one is trying to leapfrog. This is trying to leapfrog to next efficiency, right? So we're trying to leapfrog here. So minimum used E equals min used E and candidate E, right? And once it's all done, or if it's this, then we go out. Now this is not candidate E. If you think about it, it's not candidate E. Min used E is the actual E going through all this, right? It's actual E going through this. This is just at the beginning, trying to say, oh, this is the lower bound. But it could be that they are all higher than the lower bound, right? So when they come out, this has to be min used E, right? So among them, the min used E, right? The minimum used E. Speed sum plus After that, current E is going to become a min used E. Current E is going to become min used E. Then we go back up, right? We go back up. Then current E is the previous min used E. Hold on. Is it min used E though? Because after we go through this, we obtain the min used E. Now there are two scenarios, right? The min used E is very likely to be bigger than the actual min E. And we're pulling through the ones that has the largest, right? So if min used E is larger, then we already used it. So we shouldn't go through it again because that would just repeat the exact same thing. So we need to do a bisect. So let's import bisect. Let's just import bisect, right? So this is gonna be bisect dot bisect left, right, doesn't matter. I think I like to do bisect right. What's bisect right? The first one's going to be efficiency, right? And min used E. So we do efficiency, min used E. We'll find the index for the next one, right? The index for the next one. Right, the index for the next one. Index. Current E index goes to 0. And then all the current E appearance. So we have current E here, just going to be efficiency current E index. Right? So current E index. And then this current E index is going to be the one that's just bigger than the min this. And then we do this. Coming up, we can say while heap and current E index is smaller than len efficiency. Right? So we can just say current E index and len efficiency. It's called len efficiency M. right? We'll call it m. Let's say if this is smaller than m, then we can keep going. And the rest is going to be this. Speed sum, okay? And once this one's done, I'm going to return rest. Okay, give it a shot. Okay, so 3 very much the same. So I can actually copy and paste them all the same. The speed, efficiencies are all the same. Only difference is k. So the first one, k is 2, right? Now I can do this, this. Next one, k, answer is 60. Next one, k is 3. Answer is 68. Next one, k is 4. Answer is 72. I also want to throw in my test case. We have 1, 2, 3, 4, 5, 6, right? 100, 2, 3, 4, 5, 6, and 6. Answer is 100, right? So these are the test cases. So we have, oh, I forgot the n. So 6. Here it's going to be n, speed, efficiency, right? And this one is going to be max performance, n, speed, efficiency. I forgot a k. I also have a k. So this k. Try it. Error. Argument must be a list. Heap argument must be a. What, heap is not a list? What? Heap is not a list? Oh, heap becomes a generator. So the list pass. Will pass everything. But I think the logic is correct. It's just the runtime. I'm afraid of the runtime. Please don't time out. Please don't time out. It looks either wrong answer or timeout. Yeah, looks like timeout. Oh wait, didn't time out. Wrong answer. I want to pass 18. Now we hit here. Output 81. Answer is 84. Interesting. All right. It means the logic is not correct. Okay. 5, 8, 9, 5, 9, 1, 2, 6, 9, 2. Answer is 84. And my answer is 81. Okay, what is the problem? So I say I pick 1, right? And then 9, 9, 18 times 2, that's 36. So we can actually go print out each one. What do you want to do? So I want to see the current heap, right? I want to see the current heap. I want to see the result. How do I do this? So I want to print out the min used E, right? Speed sum, temp, and heap. That's it. First round, we have min used E is 2. Wait, what happened to, oh, min used E is 2. Okay, min used E is 2. Sum is 18, that's these two, right? And then temp is this, yeah, and then remaining is this, yeah, so that's 36. So I'm actually gonna do here res as well. 36. Okay, so once this is done, I remove the 1 is not getting popped. So the minimum is 2. When next come in, I used 9. Well, next one coming in, minimum current EI. Alright, hold on. Wait, current, I print minimum used E is 2. So the next one shall be 6, right? Next one shall be 6. And this is the current one. And then get out. Yeah, the current EI shall point to 6. Because I do 2 already, so it should be 6. If it's 6, then 9 for sure. It gets out. And then this one doesn't get out. And we didn't get out 5. So the answer shall be what? 14 times 6. I think I know. Which means this one is wrong. I think what we need is j equals 0, right? While j is smaller than k, right? We do this. If heap, this is blah, 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 and if this is this, then j plus equal to 1 because we used, right? If not, then j doesn't increment, and this one will pass. Okay. All right. Try it again. Try all the other things as well. Okay. All right. This is a logic error. All right. Let's see whether it's going to time out. Judge in, judge in, judge in, kept judging, kept judging, still judging. Oh my god. Oh my god. I think this is going to time out. Ha! It's still not timing out. But we got a wrong answer again. The logic still have issues. Oh my god. Oh my god, that's a lot of numbers. Oh, I forgot to mod. One, wait, what's the result? 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 7. And we're gonna mod it just to see if we get the right answer. So I'm gonna copy this, push this one in, and copy this, put this one in, run code. See how long it takes. 104 milliseconds. Ay, ay, ay. Alright, come on. Judge in. Judge in. I'm holding my breath. I think this one's timeout, right? Yeah. Well, at least the logic is correct. So time is out, but the logic is correct. So TLE. Okay, TLE, but the logic is sound. Yeah, this is probably a gigantic number. Jesus. Okay, let's see. How many did we pass? Hopefully a lot. The last one. All right. Let's see what we can do to make it faster. What we can do to make it faster. Well, there are a couple of things we can do to make it faster, as I think. So we're using heap, so there's no way we can avoid the heap part, right? So we have to do the heap part. That's that. And then we have to sort because there is binary search to find the next smallest I. So that's that. But while we are going through k values, right? While going through k values, we have to go through the entire k, because otherwise we won't be able to know, right? We don't know. Top k. Say if it's larger, then we append. I know the merge, this part takes a hit. You know, you merge, and then you also need to turn into a list. This part must take a hit. This part is slow. But what do I do, like, if I don't want to? We're not using a heap. Let's try. Yeah, let's try. I mean, it's fine, right? We can try. If we don't use a heap, if we do not use a heap, then we avoid this. Okay, let's try it without a heap. If we do not use a heap, then we need to use a class list node, right? We need to use a node def initiate self speed efficiency, right? Both are int. Just say s and e int, and then self dot speed equals s, self dot efficiency if SPD and EFF equals E, and self dot next equals none. All right, so just a simple this. So what we're gonna do, here's what we're gonna do. We're going to sort, right? We're going to sort sort S and E, right? But it's gonna be like this, and it's gonna be sorted, right? Sorted SE for SE in zip, and reverse equals true because we want the largest first, and then we're gonna say for SE in sorted, right? So I'm gonna sort it, and then we put it out, and then we're gonna have we always have a dummy list node, right? Dummy equals list node, and we're gonna give it 0 and 0. This is initial value, right? So we have a dummy node, right? And then we say dummy.next equals this node S and E. And no, we're gonna say node equals dummy, and here it's going to be node.next, and then we'll say node equals node.next. Alright, now we go through everything, so we put them in a linked list. Alright, now we have a linked list. Alright, a linked list. Linked list. So again, this is the same. We have a result, we have current efficiency, we have M. Well, this one is the same. And we sort the efficiency. That is fine. Let's actually see, like just by itself, do we time out? Oh, that could be timing out. You're running? Yeah, you're running. So we do this, right? And we're gonna have, let's while this, right? Let's while this time, yeah. While this, right? There's no temp. We just have the speed sum and min this, okay? Then while j smaller than k and node equals dummy.next. That's where everything starts, right? We need to have two nodes because we have to, I'm the pre and current. So pre and current equals dummy and dummy.next, right? While j is smaller than k, okay? So what we're gonna do? Well, with this, j is smaller than k and current, right? Current is not a none. If current is a none, then it means we have reached the end of the linked list, and there's nothing more we can give. Okay, so in this case, because it's sorted, so we can say candidate S, candidate E equals current dot speed, current dot efficiency, right? And we say if candidate is larger or equal to the current efficiency, then speed, do this, right? And then if hold a sec. So we say if it's larger or equal to, then we do this, right? then we say if candidate E is smaller or equal to this, right? If it's smaller or equal to, then we remove it. Or we remove it, right? We remove it. How do we remove it? We have a pre, we have a current. So the current needs to be removed. Now to remove current, we say pre.next equals current.next. Right? So that's remove the current node. Yes, let's remove the current node. And then what? So we remove the current node, and we need to put the current node. So pre.next equals current.next, and current equals current.next. So current equals current.next. So this is moving to the next node. So we're now moving to the next node. So the node in the middle is getting severed, right? Is getting severed. So that's candidate E is smaller or equal to. Yes, after that, we don't need this, right? Then we say minimum used E equals leapfrog. So leapfrog needs to happen. These two shall happen higher up. They shall happen here. Right? So candidate E is larger, right? Then we need to record the minimum used E and we increment j, right? We increment j because we used j. If not, then we just remove it. Yes? And we also need to move, because we move it here already, right? We move here already. That means we have to move here as well. So move here shall be fairly simple. We only need to do, so j plus equal to 1. Then the current we have visited, so we say current equals current.next. And pre equals pre.next. No, hold on, that's not what we want. That's not what we want. No, because this is just a check, right? It's a check. After checking, if the candidate E is larger or equal to, so we do this. And then we say candidate E is smaller or equal to, we remove, right? After we remove, we already move the current to the next, which actually I don't want to do, because I want to move, so I will do it here. Pre equals pre.next. Current. Hold on. So what we say is if candidate E is smaller, then we need to remove it, right? We remove it and move it to the next, which means if candidate E is smaller than equal to this, so pre.next equals current.next, we're removing this, and current equals current.next, so current move on to the next one, right? And pre stay where they are. Pre stay where they are. So we can say else. There we go. So this is just to record, right? After recording, we decide how to move. This one is to remove, right? After we remove, pre stay where they are, so we move current up. If we don't remove, then pre move forward, and then this one is this. Okay. So this, after this, so this is remove nodes if efficiency. If efficiency has been covered already, right? Then move to the next one, pre move to the next one, current move to the next one, and go back up. Again, j is smaller than k, and then we know that if it's smaller, then we don't do j, right? We don't do j. Yeah, and we just remove it and we'll keep looking for the next one. So j is smaller than k and current. When we're done, we do the rest. After the rest, we just find out, and we don't need to do this. Okay. Let's try solution 2. Generated expression must be parenthesized. So this one has to be parenthesized, which means we need to put this sorted. Nope. It's not correct. Okay. Why is that? Why is this not correct? Let's do one of them just to check. So one step at a time. Let's just say here, right? Node equals dummy. Next. And I say while node print node dot speed node dot f node equals node dot next. 10, 4, 8. Yeah. That's correct. Okay, that's correct. So node is fine. Efficiency is also short, 0. Okay, so minimum efficiency is this, j equals 0, blah blah, right? And I think the thing is rest is 0. Current dot speed, current dot efficiency, right? And check print candidate S and candidate E. Okay, yeah, we have something printed out. If candidate S is larger or equal to efficiency, then sum. Oh, I see. There's no more minus. Everything is positive. Then speed sum will be negative. Be all negative. Yep. Now we pass. Now we all pass. Let's try. This is a linked list. Linked list solution. If this one still time out, I'm going to check the correct answer. Alright. Come on, man. I lost the test case that I want to try. Dang it. Alright, try it. Pending. Judging. Doesn't look good, huh? I think it's gonna time out as well. I thought it's gonna be faster. Ah, shoot. Alright, so I think it's the method itself. The method itself has issues. Yeah. I'm pretty sure it's gonna time out just by building the linked list. Yeah. Not even going through it. Maybe like building the linked list, we're gonna time out already. Like we don't even do this. Like the meat part, it's not even there. Like just this, just by this, probably is gonna time out. Oh, it's not. That's not a problem. Yeah, it's fine. Problem is this part. But I'm pretty sure that current EI is incrementing. What if we don't leapfrog? If we don't leapfrog, so because the thing is we have a log n here, right? We have a log n here. We will leapfrog whenever we need to, right? If we don't leapfrog, then because this is O log n, this is O log n. Now we can make it even faster by passing the, because we know it has to be bigger than current EI. So I think bisect has this. Bisect, I think it has, you can pass in a low and high. Yeah, I think I'm passing a low, so we can do a low. So we can do a low has to be min no has to be current EI actually plus 1, because it cannot be current EI, it has to be current EI plus 1. I think this is still a timeout, but I think it might be a little bit faster. Yeah, we don't know. I think the thing is, there's no leapfrog. Like, we're not leapfrogging a lot. Because we're not leapfrogging, so we're doing this every single time. So what if we don't leapfrog at all? Right? If we don't leapfrog at all, then without changing too much, right? Without changing too much, without changing too much, we can just say for current EI in range M, right? In range M, and then this OM, there's no log part in it. No. Still no good. The fundamentally something is not right. Let's think a little bit, just a slightly little bit more. I think we are computing more than we need to, right? The efficiency, right? Efficiency. Now we'll leave in the leapfrog. The leapfrog already guaranteed, right? The leapfrog, we already guarantee that we're going to skip a lot of the things that's not, that we already skip based on the current thing. We already skip. Hold on, I need to double check this one is actually correct. Oh, oops. Yeah, the bulk is M times K. And we know M is huge. This is huge. And K is also huge. So that's why this is not going to work. We have to reduce it to, like, not go through all K. But there will be things that we'll remove. That's the thing, like, we'll remove stuff. Let me think about it again. What do we have? We have 10, 4, right? 8, 2, 5, 7, 3, 3, 2, 5, and 1, 9. That's what we are dealt with. That's the first one, let's say. We get 10, 4. So we know we have 10, 4. But that's, we're not guaranteed 10, 4 is the biggest. So we just say current is 10, 4, right? And then we have A2. I don't know. All right, let's not waste time. Let's go to the answer. We're gonna admit defeat. We have two solutions, but both timeout, TLE as well. It's fine. It's fine. That's fine. All right, let's take a look. Gotta be. Oh, wait. We have hints. We have hints. Keep track of the engineers by their efficiency in decreasing order. Oh, efficiency in decreasing order. And then what? Starting from one engineer to build a team, it suffices to bring k minus 1 more engineers who have higher efficiencies as well as high speeds. I think this is the same idea. Like we go from the minimum efficiency, and we just need to bring in the remaining that have higher as well as high speeds. I think isn't this what I'm doing? Isn't this what I'm doing? I'm going from the smallest Let's try this one again, but let's say we do not leapfrog. If we do not leapfrog, like we do not leapfrog, then we just say, I mean, we can do like another check, right? So we can just check to see if it's the next one. Right? If it's the next one, then we do not need to leapfrog. So we just say it's the, also we're gonna say low equals current EI, right? And we're gonna say if min used E is equal to efficiency current EI, then current EI plus equal 1. Else current EI is going to be this, and we have to merge. So I add a little bit just to make sure that we don't have to always. But I feel like it's still gonna time out. It's just like micro upgrade. It's not gonna work. Yeah, no, it's not gonna work. All right, let's check. I think we're on the right track, right? We are on the right track. It's just we don't know what data structure to use to make this work. All right, show me the data structure. Maybe a better logic to get this one to work. Okay. Do we have a solution? We do. Combination problem, meaning one could enumerate all possible compositions to return a team with a maximum performance. However, this brute force idea is intuitive, is also inefficient because the number of combinations grows. Yes, some insight that can be derived, and we can speed up a greedy algorithm, the application priority queue, greedy with priority queue implementation. So use n times log n plus log k. Question is more of just sailing through, and then a really trick. Oh, some people say it's a. My God, he said it's not a hard one. I got stuck. I got royally stuck. Holy moly. Anyway, I didn't put this as nightmare because I wasn't able to figure it out. Sum of all, multiply, The performance of a team depends on two variables. Let's fix the value of one of, yes, minimum efficiency. That's exactly what I was doing, minimum efficiency. Key idea behind is this. For each candidate, we treat him as the one who has the minimum efficiency, yes. We set the rest of the team based on this condition. Yes. The optimal solution to the problem. Yes, I might know that. This helps prune some of the unnecessary team privilege. Yes. Fixed candidate and only accept the new team members that have higher efficiency. Yes. Size K. Enumerate all teams of size 1 to K. Yes. Each new member is guaranteed to. Yes. I think I just need to see your algorithm. I think the idea is the same. Let's see a Python solution. Let's see, where did I go? Oh my God. Why do you always have so good? Right, we're gonna zip it. We're gonna sort it. Okay. So sort by their efficiency. Bless you. Efficiency reverse true. So high efficiency at the top. Speed heap, speed sum, performance. Current in candidates. Maintain the heap for the fastest k-1 speed. This one's larger than this. Speed sum minus equal to heap q at top. Push. Hold a sec. We put the heap on k. How big is k? K is smaller than n. We put a heap on k instead of put a heap on. Okay, so in candidates, why is reverse true? I thought we're going from the worst. I thought we go from the worst. This would be the smallest first, right? Anyway, let's keep reading. Maintain a heap for the fastest k-1 speeds. If len is larger, then we have k-1 fastest. So we just want to keep the k-1 fastest. Then if len, we sort by efficiency, and if len this is larger than k-1, then we're gonna pop So we pop the one with the slowest speed, and I'm going to push the one with the current speed. So we're saying the current speed is faster. And speed sum minus current speed sum plus the current speed performance. I think they got it wrong. It should be speed efficiency instead of efficiency speed. We're going to sort based on speed. Okay. All right, let's forget about the linked list. It's not going to work, right? Because I think linked list, you're trying to do it yourself. It's just going to be slow. So let's just focus on this. So this is the idea I have, which is, I want to say almost the same. So I did realize we need to start from the lowest efficiency, right? So we start from the lowest efficiency, and as we go through the lowest efficiency, what my idea is to go through to have the, because it's m times k. Mine is n times k, right? But here is n times log k, because here I'm going through each and every, I'm going through k candidates. I'm going through the top k candidates, right? But what they're going through is they go through each individual candidate, right? And hold on. I think this is slightly different. They just go through it once. They go through it once, every candidate. They go through every candidate, right? They go through every candidate, and they want to see for this current candidate. The current candidate, what is the speed that we have? Performance is speed sum times current efficiency. This current efficiency is the smallest, so we go through them. So we'll go through all four. It's different. Have the same concept, but actual thing is different. Okay, so for them, what happens is we sort the entire team. We put a small efficiency first, right? So low efficiency to high efficiency. So every time we get a team member, right? Every time we get a team member out, we put the speed into a heap, right? And then we do these things, right? We compute these things, and then because currently the base is the current efficiency, that's the smallest efficiency, so we can always add the next one, right? We add the next one, so we add the next one to see if it improves. We add the next one to see if it improves. Once we add k, that's the first k members whose efficiency are the lowest, right? So we put them together. So that's the base, right? That's the base. Now I put in more, right? I put in more people, right? More people. So next one comes in. Now the speed heap is larger than k minus 1. So I'm going to pop out the speed. I'm going to pop out the speed. So I pop out the slowest speed, and I push in the current speed. Are you saying the current speed is larger you're saying the current speed is larger than the previous speed, but you're not sorting based on speed. You are sorting based on efficiency. Or are you saying you're actually sorting based on speed? If we sort based on speed, then how do you guarantee? I feel this one is not right. How do you guarantee? So you're saying we maintain a heap for the fastest k-1 speed, right? That's what you say. The fastest k-1 speeds. And then you sort the candidates based on their efficiency. And you sort with the worst efficiency first. Yes, if I put the worst efficiency first, then every time I get a new one, then that one must be the current efficiency, because this is the current lowest efficiency. That is correct. That is correct. Okay, we solved that part. How about the speed heap? So we push the speed in, and if it's larger than k-1, then we pop. Why? Why do we pop? Why are we saying that the next speed is going to be larger than the previous speed? Well, it's actually not. It's actually not. I think, yeah, no, this is just, we have to, again, one more time. So what we doing here is because we have to include the current speed. Therefore, we're going to pop the previous speed. We pop the smallest of the previous speed. That is correct. We pop the previous smallest speed. So now, when we add our current, so that's in this order. In this order, as we go through, we maintain the fastest it's actually not k-1 speed, it's fastest k speed. It's fastest k speed because large that means that equals to k, so we pop k and then we add, so it's k, so it's the fastest k speed so far, including the current candidate, right? So including the current candidate, and we have that is true because the current candidate has the lowest efficiency, right? So because everybody else, so we say if we want to include the current candidate, then the efficiency will be him, and then the only chance is to add the speed whose efficiency is higher than him, and we need those speed that's the maximum. Yes, that's exactly my problem. I want to find the maximum too. We have the current candidate. No, we have the the current efficiency, the minimum efficiency, and we want to find everyone whose speed, anyone whose efficiency is larger or equal to the current efficiency, and we record this, the candidate, the speed, and we add the speed together, right? So that is the same, but the difference is, well, I am at it, I find the minimum efficiency, and I loop through either priority queue or a linked list. I loop through it to collect the maximum, right? To collect maximum. And the thing is, every time I have to collect k times, right? We have to collect k times. So next time go up, I have to collect k time. Next time go up. Every single time I have to collect k times. But in this scheme, we sort it such that we know, so this one we sort by sorting efficiency, highest efficiency first. We know that all possible candidates are the ones to the left of me, right? Which means all possible candidates have already been visited. So, therefore, we can keep a priority queue on all the candidates that have been visited before to maintain the maximum. Now, this is slightly different, right? Slightly different. I am not looking for the max of the max among the entire team. No, I'm only keeping tab on the max of the ones that's possible to me, right? Now the benefit is obvious. We have to do n times here, no problem. But here I have to count k times. But here I don't have to count extra. There's no need for me to count extra because we're doing the counting every time we visit. Every time we visit, that is a candidate. But every time in here I visit, we don't have a candidate because we haven't sorted yet. Yeah. I got it. It's a very, very good question. Very, very good question. Yeah, I think I agree. This can be a good interview question. I agree because you at least need to come up with the ideal of fixed efficiency. But the implementation, yes, all possible candidates are to the left of me. That is intuition. So we don't have to go through them every single time because I already go through them once. Good question. This is a good question. Very, very good. Very good. Okay, so let's do it. Let's code this ourselves by going back to challenge. I understand how this one works. It's a little bit unfortunate that we're not able to solve this one, but we have the solid foundation, and we'll have to say the official solution. I'm going to provide a link to the official solution. I think it's submission detail problems. I think it's here. Oh, it's here. So we don't need this. No. Okay. So I want to post this one here. The official solution. The basic concept is exactly the same. We fix the person with the min efficiency, and then we find the k people whose efficiency is larger than the currently fixed one, and also have the max speeds. The difference is that the solution uses a very smart way to ensure that we don't have to traverse k times for each fixed efficiency. They sort the people by efficiency in reverse order. Thus, for each current efficiency, the people with higher efficiency are the ones that have been visited before. Then we only need to keep a heap. Keep a heap on the visited people. Keep a heap of size k on the visited people to ensure that those k people have the highest speed. In my implementation, for each fixed efficiency, I have to iterate k times to find the k maximum, speeds. Although I am already pruning, the runtime is inevitably O, NM, O, N, K, but with the official solution, since we already traversed, all the possible candidates, we only incur log k for each fixed efficiency, and thus reaching O n log k in the traversal. The final runtime is O n log n plus log k, where the first O n log n is for the first O n log n is for the sorting. Okay, so we can do this. Sorted f equals sorted reverse equals true, and then this is going to be efficiency EF. Now I'm going to do a speed. I have speed efficiency for SE in hold up. For SE in zip speed efficiency. Actually, I think this sort already sort based on the. I think so. Not 100% sure, but I think. Let's say 4, 1, right? 3, 2, 2, 3, right? Let's see. Sorted A. Give us 2, 3, 3, 2, 4, 1. Yeah, I already sort based on the. Already sort based on the first key, right? Sort based on the first element. Now, after sort, we're going to say speed heap. Yes, speed heap is this, and the rest equals 0. And we're going to go for SE in sorted F, right? If len speed equals K, right? We need to add the current one in, because current one we have to always have it. So current one has the smallest efficiency among everybody we currently have so far. So what we do is we're including this, and well, what if we have those repeating situations? If we have those repeating situations, no, it's fine because we're keeping the maximum. Yeah, we're keeping the maximum, so no matter what, the efficiency is there, and we keep the maximum. Yeah, this is good. This is good. So we didn't say also speed heap. We also need a speed sum, right? I'm gonna say speed sum minus equals to heap q dot heap pop speed heap, right? And then we say heap q dot heap push speed heap and the current speed, and speed sum plus equals current speed, and res equals max res efficiency E times speed sum, and return res. Okay, let's say this is solution 3. Hey, we have failed. Something is not right. Something is not right. What happened? Speed sum plus equal to S. Yeah, we pushed in. Current efficiency is always the smallest. Hold up, let's see. Let's take a look. We're gonna first print out the sorted efficiency. So yeah, sorted efficiency. No, yes. I know why. Yes, so yes, it's sorted based on the first element. Now we pass. Very good. So, I think this is a way of thinking. How do we find the top? Hey, wrong answer. What the hell? Oh, keep forgetting about this. 1, 2, 3. I have this. Kept forgetting. Yeah. So this ideal is just to. Yeah, we passed. The ideal is to keep track of the top k largest values, largest speed, right? Keep track of the top k largest speed. Now my way is to iterate through a sorted list that will iterate k times. So that's how I keep track of the top. But it's slow because it's have to do k times. Now the fast way is to keep all the candidates are the one that we have visited before. And each time we visit a candidate, we push it into a heap. Then we can use the heap to keep the fastest, to keep the top k values. Basically, every time a new value comes in, that we encounter a new value, we pop the current smallest, and it will push into the new one. Now, that's the issue. Like, we need to push in the current one, even if the current one is not a big one, because we're saying we're including this efficiency. Basically, we're saying what's the maximum value when we have to include this engineer, like this person. So we have to. Very good question. Very, very good question. It's fine. Alrighty. Man, nothing from the discussion. Priority queue. Oh, minimum cost to hire K workers. Binary insert. Reverse equal 1. Oh, shoot. Ay, ay, ay. That's true. We can just zip. Ah, Dios míos. We can just do this. Ah. Yep. Ah. That's correct. We don't have to do this. Yeah, we can just say sorted this. And that's it. And then we do efficiency first, and then we do speed second. Wow. Yeah. I didn't realize. Min heap solution. Okay, well, that's it. Formal proof of correctness. I mean, you don't have to really prove. We know it's correct because each person has a chance to be included in. Each person has a chance to be included as the least efficient member of the team, right? It's possible. Each person has the possibility. So we say we took all these possibilities. We have n different possibilities. Right? Each person as the min. Then the question becomes, what are the team members this person can find? Well, the only team members this person can find are the ones with higher efficiency than him. And among those with higher efficiency than him, we need to find the ones with the highest speed. And that's it. That's it. Okay, that will be it. Well, we didn't solve it, but it's a good exercise. Kind of, I guess if similar question happen again, I will struggle as well. But hopefully, this idea of using priority queue to keep track of the top k. Now, don't just iterate through k. The top k values, the highest values, using priority queue to track. This is a good trick. Very, very good trick. Alrighty, that's it. That's it for today. I'll see you guys tomorrow for another difficult one. Adios.